Hi, welcome to Mr. Hamilton's Math Bites. This video is about function notation. Our goals for today will be twofold. First off, we want to identify what function notation is, and secondly, we want to represent linear and quadratic functions using function notation. So the first question is this: what do we mean by f of x? That is what function notation is right there, f of x. Recall that a function is a relation in which there is exactly one value in the range for each possible value in the domain. There's only one y value for each possible x value. We can think of a function as a machine that does a particular mapping. That is, it maps each possible input value to the corresponding output value using a specific value, specific rule. So, for example, if I put 5 in here and I get out 9, every time I put a 5 into this input, it's always going to give me a 9 out again. Likewise, let's say that I put a 7 in the input and it gives me 11. Every time I put a 7 in, it's always going to give me out an 11. Imagine for a minute that you are a kid again and playing with Play-Doh. And we put a little ball of Play-Doh in our little machine, and what it does is it spits out, you remember this, right? It spits out a little rolled up chunk of Play-Doh. So every time I put that much Play-Doh in, I'm going to get the same length out. If I put a bunch more Play-Doh in, drop that in there, I'm going to get a lot longer of a piece of Play-Doh out. So it's the same idea with numbers here. That's what a function does. It is a machine that does a particular mapping. Always gives you the same results depending on what you put in it. You put the same thing in, you're always going to get the same results. There are infinitely many different ways of mapping out inputs to outputs. So there are infinitely many possible functions. We can define a particular function by giving it an identifying letter and specifying the rule that the function uses to map its input to its output. For example, we could define the function f of x equals 3x plus 5. This is really the same thing as y equals 3x plus 5, but with this function notation. In this definition, f is the name of the function. It distinguishes it from any other functions. Suppose with me for a minute that we had fx equals 3x plus 5, and we also had this other function, 4x plus 6. Well, if we didn't have function notation, you wouldn't be able to differentiate very quickly or concisely between those two functions without saying the one is y equals 3x plus 5 and the other one is y equals 4x plus 6. But if we turn the y equals 3x plus 5 into function notation and we turn the y equals 4x plus 6 into function notation, we might name the second function as g of x equals 4x plus 6. So then all we have to say is I want f of x, not g of x. It's a lot shorter of a way to say that. The x in brackets following the f tells us that the independent variable of the function is x. Where's my cursor? So sometimes you might have a different variable if the independent variable is something like t for time or d for. Note that f of x does not indicate multiplication. It is the output value of a function for which x is the input variable. And lastly, the equal sign tells us that what follows is a rule. The function is used to map the input value to the output value. We can name a second function g of x, as I described above already. We can also name a third function h of x, and specify them with different rules, in other words, different equations. This next section's a little bit wordy, so I'm going to underline some key things as we go through this. But I'll read through it as we go here too. We can use the same kind of notation to represent the output value of the function for any given input. The desired input replaces the x in f of x, so instead of having f of x, we might have something like f of 2. Thus, function notation gives us a shorthand way to indicate that an expression is to be evaluated. So, using the example function definition above, f of 2 means the same thing as the value of the expression 3x plus 5 when x equals 2, but it's much easier to write. I want to underline that for you. This is the same thing as saying this. Obviously much easier and shorter to write. And say, given that the function is f of x equals 3x plus 5, we find f of 2 by simply substituting the value 2 for each occurrence of x on both sides of the equal sign. Remember to use brackets around the substituted value when substituting into expressions. We will have the following. Watch this. I don't think you'll have much difficulty grasping this. I've substituted 2 in for x on f of x side. And on the other side, I'm going to substitute 2 in for x as well. So I get 6 plus 5 is 11. So we would simply say that f of 2 equals 11. That is the same thing as saying the value of the expression 3x plus 5 when x equals 2 is 11. Now determine f of 2 over 7. Always keep your answers exact. You go ahead and do that and compare answers with me as I get there. We need a common denominator. That's like it's over 1. So if I multiply both the numerator and the denominator by 7, I'll get that common denominator. So what we have here is 41 over 7. The input to a function doesn't have to be a constant value like 2. It can be any expression. So if the input to a function were 2a plus 3, for example, we would find the output in the same way as above, substituting the expression 2a plus 3 for each occurrence of x. Let's do that. F of x equals 3x plus 5. So that means that f 2a plus 3 is equal to 3 times 2a plus 3 plus 5. We've replaced x with 2a plus 3. Now I can use the distributive property to expand this out. (6a plus 14). Note that in this case we can't come up with a numeric value for the input of a function because we don't know the value of a. The function is therefore called an expression, not a number. Lastly, let's move on to graphing a function. Suppose we were asked to graph the function f of x equals 3x plus 5. We know that's a linear relation. Remember that x is the independent variable of the relation, and f of x is the dependent variable. In other words, f of x is really like the y. On a graph, we plot the independent variable on the horizontal axis. So the x value is going to be on the horizontal axis, and the dependent variable, the y value, is going to be on the vertical axis. So the graph of f of x will look just like the graph of y equals 3x plus 5. No surprise, no changes there. The only real difference is that on the y-axis, instead of x, we have f of x. We can use the graph to find the value of the function f of x for a given input value. For example, if we were asked to find f of 1, we would determine the dependent variable value when the independent variable had a value of 1. For example, f of 1, there's my value of 1 right there. And if I go up with that, this isn't a great graph, but it's fairly close. You can see that the value of 1 corresponds with a y value of 8. So we would simply say f of 1 equals 8. as you have typed right there. At the end of this lesson, I always get questions where people ask, why are we using function notation? So if it's not clear to you already, here's the summary. Function notation is really a way of writing things shorter, and that's really what math is about in many cases. Because things are so long and so drawn out that if we can shorten things, that makes our life easier. So it allows us to do three things. It allows us to clearly and efficiently distinguish between functions, f of x, g of x, h of x, etc. It allows us to have a short form for the value of the function 3x plus 5 when x equals 2. That just becomes f of 2. And lastly, it allows us to quickly distinguish if a relation is a function. If it's written in function notation, we know right away that it's a function.